fourth cousins twice removed.
Yeah, something like that. I never learned that. What's other? Okay. So Rob is a Charles River professor at School of Engineering and Applied Sciences at Harvard University. He is one of the core founding faculty members of Wyss Institute of Biologically Inspired Engineering, and he's a national geographic explorer. He got his PhD from University of Berkeley, and since then he has won many awards, a list of which I have here, and it's not a complete list, and I cannot go through all of them, so if you're interested, just go check. What else? Oh yeah, so there's something that I want to tell. So apart from his groundbreaking research in micro-robotics and soft-robotics, which hopefully you will listen more about soon, the most important thing about him is that he inspired and helped many people like me to find our way in academia and industry. So I'm excited to listen to Rob, and let's welcome him.
So thank you, Zeynep. It's a pleasure to be here again. I'm going to say a little bit about the work that we do in my lab. I was trying to think of a common theme to sort of thread everything together for the stuff that we do, and the best I could come up with was borrowed from one of my former students, Peter Whitney, which is the mechanical side of artificial intelligence. So I'm going to start off by some brief definitions, which hopefully illustrate this. And then the best thing I could think about doing instead of sort of giving you strict definitions over and over again is to illustrate by example. So I'm going to give it a few examples of some of the work, some of the projects that we're working on in our lab. But to start off, artificial intelligence. What is artificial intelligence? This is not something that's new to any of you, but it's the theory and application of computer systems that would do things which would normally require sort of human level of intelligence to do. So this is something that is not a new definition. It's something that was coined at MIT back in the 50s, so it's rather old. This is not what we do, okay? So more along the lines of what we do, I define it as this. So development of the mechanical side of artificial intelligence, the development of systems, of robotic platforms that make challenges for perception, control, and autonomy easier by virtue of their mechanics, materials, manufacturing, design. So building platforms which alleviate some of these more classical AI challenges. I'll come back to this later on, and there's many names for this: morphological computing and embodied intelligence, whatever you want to call this. But I'll argue that this concept is far, far older than what we think of as classical artificial intelligence. But again, I'm not just going to sort of rant at you about what I think that my philosophy about this is. I'm going to show you by example. So I'm going to do 3 examples. The first is in small-scale robotics, so robotic insects. The second 2 are going to be then in soft robotics. So the second one being soft robotics for the deep sea, a relatively new set of topics that we're working on to try to sample, manipulate, interact with organisms at the bottom of the ocean. And then the last one is how can we build entirely soft robots. So first, I'm going to start with some robotic insects. So this is a project that we've been working on for quite some time. It's the development of things like this. This is something that's it's just what it looks like. So this is a 2-wing, flapping wing robotic insect that requires us, if we wanted to create something like this, one of the reasons we like this project is that it requires us to think about all sorts of things related to fluid mechanics, related to microfabrication, actuation. How do we create small-scale artificial muscles which would act to flap the wings? How do we understand the fluid mechanics associated with how the wings are moving and generating and manipulating vortex structures in the air? How do we think about control for severely underactuated and highly dynamic, unstable systems? How do we think about new sensor networks, new computational architectures, power systems, coordination algorithms, et cetera? So this is the reason that we like this project is because given the size, weight, and power constraints for something like this, there are no off-the-shelf solutions which would satisfy this sort of the goals of this sort of project. So I'm not going to say much about the applications for something like this, or utility of something like this. You can imagine many, some good, some sinister, but I'll just show one here, which is something in assisted agriculture where you might have hundreds or thousands of these things operating collectively. the arguments about why you might want to use a system like this for these sorts of applications, or if it's not this, then search and rescue or hazardous environment exploration. The arguments are very similar to what I would say for anything where you wouldn't want to put a human or an animal. If I want to have something that's too tedious or dangerous or whatever, maybe you get some economies of scale by having something smaller, something cheaper, something that has sort of duplicity, many number of these agents. Maybe you get some graceful degradation to failure of any individual. Maybe you get different perspectives, et cetera. I'm not going to really get into that. What I really want to get into is the sort of answers to some of these questions that I posed earlier that we have to answer, that we have to solve along the way. So the first one is in how do we build stuff like this? And so this is something that we've been working on for quite some time, going back to my PhD at Berkeley. This is an example of, I would say, how not to do this. So if I wanted to make something on the scale of an insect, then I probably don't want to do something with hundreds or thousands of arbitrarily shaped components assembled. The assembly would be very tedious, would be very difficult, require a great amount of dexterity and skill, et cetera. This is an illustration of the internal combustion engine from a Ducati motorcycle. So again, this is sort of the what not to do. Now I'm going to contradict myself, because this is how we started doing this assembly of these devices. This is what we'll call the old way. This is another name for this sort of process is graduate student with tweezers process, which is just basically it's exactly what it looks like. So I'm assembling, this is sped up quite a bit, but I'm assembling all of the components of this robotic insect, a couple of actuators here, a transmission mechanism here, wings, whatever, all by hand under a microscope. Takes a tremendous amount of skill, takes time. You can't just walk off the street and do this. It takes time to build up these sorts of skills. And the subtle thing, but is very important, is that if I do things in this way, where it takes maybe a few weeks to a month to build an individual robot, I'm really not exploiting the rich design space that I might otherwise want to really study. We know very little about the sort of physics and fluid mechanics of these devices, and so what we really have to do is build and test and build and test. So we want a process which not only solves challenges associated with the scale, but also is very fast. And so we in order to resolve this issue, a few years ago, we sort of racked our brains and started to come up with ideas, looking for inspiration wherever we could. And one of the places we found inspiration was from Richard Feynman, Nobel laureate Richard Feynman's famous speeches from the 1950s, where he described plenty of room at the bottom. He described, prophesized, if you will, the economies of scale that you get by having small-scale devices building replicas of each other, taking advantages of the physics of scaling. And he really sort of prophesized all of this work, and not just our work, of course, but all the work in microrobotics and a lot of MEMS as well. The other side of the story is that we took inspiration from my son's library at the time, which was stacked with Popup Books. And so we created a process which sort of mimics some of the key features of Popup Books. What do I mean is, well, if I think about a Popup book, then I think about something where I turn a page, I open something, I push on something, I pull on something. Very, very simple input actuation, and typically maybe 1 degree of freedom, maybe 2. But that input motion is then coupled to this sort of fantastically complicated structures that pop out of this, and mechanisms as well. And so we took those two and developed a process that sort of looks like this. And I'm just going to gloss over it. If you want to discuss in more detail, I can talk later or point you to some papers that describe in detail some of the recipes for this. But we basically start with two-dimensional materials, sort of flat, thin materials. And these could be any material. And I'll go to the real thing here for a minute. Composites, polymers, metals, ceramics, doesn't really matter what the materials are. We come up with sort of two-dimensional form factors for these laser micromachines, so bulk micromachining the individual layers, laminating these together, and we do this via pin alignment, so we actually machine in fiducial markers as well that allows us to sort of stack and bond these layers together to create this sort of quasi-two-dimensional composite. And this is sort of akin to a multi-layer printed circuit board, but now the trick is that we are also able to micromachine adhesive layers as well. So we can control wherever we're bonding layers together through the thickness of this material. And that allows us to create, along with the ability to create structures with any sort of material composition, that allows us to create parallel mechanisms through the thickness of the device. So we can create 4 bars and 5 bars or whatever built into the layers of these devices. And these devices could be many tens of layers thick if we wanted. And then all that we do at the end, and what we were just seeing in this video, was at the end of this process, then we've got our structure. And the way that this works then is by simply in the back, in this demonstration is just going to be pushing from the back with pins, then all of the trajectories that would move a wing to align with a transmission or an actuator or an airframe or whatever are all just controlled by the parallel mechanisms that are built into the thickness of the device. So we don't have to do anything. So it's sort of a self-assembly where we just give it one input actuation that's mapped to all these other motions. So just like a pop-up book. And then we pluck out the thing. Once we pop it up, we freeze it. And again, I'm glossing over some of the details. Freeze it, put it back in a laser system, cut out the part that we want, and there's our robot, and throw away the rest. Okay, so this has a number of nice features that I'm not going to really dwell on. A couple things I will mention is that we can make anything, any mechanism or any structure. Again, we can use any material. The other nice thing is we basically, like I said, made a multi-layer printed circuit board so we can fabricate circuit elements directly onto these two-dimensional composites prior to folding, and then pop up and you have this sort of monolithic electromechanical devices. We can embed actuation that way. We can embed sensing that way. We can embed computation or power that way as well. So as of a couple of years ago, this is what our devices that we were able to construct look like. I'm not going to get too deep into the design of these things, but I will tell you a little bit about their function. And I think this is where the first example of this thesis of the mechanical side of artificial intelligence sort of comes up. So we worked with biologists a long time ago to sort of study, this was around the late 90s when Michael Dickinson and his crew were really developing the first evidence of how what they termed non-steady effects, unsteady effects, were being developed by flapping wings and then manipulated, and how they sort of overcame these uncertainties with respect to how flapping wing insects are actually able to produce enough thrust to stay aloft. So they had these fantastic dynamically scaled models that were able to really experimentally study this phenomenon. So bottom line is we took away from that. If you have some notion of the wing shape that you want and some notion of the kinematics you want to achieve, in this case 2 degrees of freedom, so a flapping motion and then a rotation motion about an axis that's roughly parallel with the span-wise direction of the wing, then that's what we need. We need these 2 degrees of freedom. We need to do it at a fairly high frequency. One of the things that we do for this is flap at the resonant frequency, the coupled resonant frequency that's mostly dominated by the inertia of the wings and the stiffness of the actuator mapped through a flexure-based compliant transmission. But if we think about these 2 degrees of freedom, then that's what we need. As a sort of naive roboticist, the way that we started off thinking about this was, well, if I need 2 degrees of freedom, then I have 2 actuators, and I have some mapping, some, let's say, differential mechanism that maps these 2 actuation motions into this desired flapping pattern. It turns out that would be, for a resonant system, you'd have this coupled 2-input, 2-output system that would be very, very difficult. You'd be throwing away a lot of energy into fighting one mode or the other when I'm trying to achieve this flapping motion. And so we got away from that, and the long story short is one of these modes is passive, and we make that mode quasi-steady just by putting the resonant mode of the rotation well above what the flapping resonance is. And so we get this sort of nice quasi-steady flapping and rotation motion just with one single input, and that's what's being illustrated here. The other thing that's being illustrated here is we sort of split the bee into the robot into 2 halves, and we actuate each half independently, and so we can achieve what we call roll by doing amplitude modulation on one side with respect to the other. So if we have for a fixed frequency again, if we have a greater amplitude, we have a greater velocity, the lift roughly goes as velocity squared, and so we can get greater lift on one side than the other, and we produce what we call a roll. Same pitch is very similar. We just bias the stroke fore or aft with respect to the center of mass, and then yaw. It's a little bit more complicated because we have to do, again, we keep the period the same, but we flap faster on let's say the upstroke and slower on the downstroke, so you get this sort of asymmetric drag. Okay, so we can do that, and then I just want to illustrate this just to sort of show off a little bit gratuitously like the level of complexity that we can embed within these devices. So this is an example. I'm not going to go into the details of what this is. This is an attempt by a former student to actually embody more controllable degrees of freedom within a device like this. And this consists of, I think it's 2 planar 4 bars, 2 spherical 4 bars, or 4 spherical 4 bars and 2 spherical 5 bars, all within something that's a couple of cubic millimeters. That's sort of zoomed in here to see the rich structures that we can achieve with this. Okay, now we've got these devices, and hopefully you trust me that we can make these things, and we can mess around with the designs sort of readily. It's sort of commonplace now to build one of these devices, and yes, now you could sort of walk in off the street and follow recipes and build one of these devices, so no problem. Now the next thing we tried to figure out was control. So this is done in a way that we think about sort of like training wheels, where we have a motion capture environment, just as you all are no doubt familiar with, although not in a room this size, it's about this size. And so we can get very high spatial resolution, very high temporal resolution with low latencies. We just basically tweak the system until we can get latencies on the order of a few milliseconds, such that we don't mess around with our controls. Here's what this system looks like, and there's the device under test. If I just take the device sort of off the assembly line, so to speak, and plug it in, this is what happens. This is, mind you, this is slowed down by a factor of 8. And so this is what happens. It's highly open loop, unstable, and this is what you're seeing is a sequence of sort of training flights where we, despite our best efforts at fabrication and having a precision within all of the assembly of the components of the devices by virtue of the processes I was telling you, nonetheless, there's still some asymmetries that arise, and that sort of triggers these instabilities. And so this is what happens. This is what it looks like in real time. So it's a rather fast process. So, but once you can close the loop, and we do this in a number of ways that, again, I'm glossing over the details, but we can, by using this sort of motion capture system and by having all of our control electronics off board, you can see the tether here, then we can use this as training wheels. We can prototype whatever controllers, we can emulate whatever sensors we want. We can do, for example, simple PID control actually works fairly well if you do it fast enough. We can do adaptive control if you want to learn some of the unmodeled dynamics, which is something that's very effective. And again, because there's so many things about this system that are unmodeled. You can do sliding mode, repetitive control if you want to sort of have something which nicely rejects oscillations, periodic oscillations from that arise from the flapping wings. So you can do whatever you want. And one of the interesting things that is sort of illustrated here is that although there's a lot of challenges operating at these scales, we do get some benefit. One of the benefits we get is just illustrated in this, in that we don't really ever sort of gracefully land the things or have any safety. There's no nets around this. We just turn it off and they crash. So by virtue of their physical scale, these things are naturally robust. Things get more robust as you get smaller, and this is something that's been known in the biological literature for some time. All right, we can get, partially because of that and partially because of the relative ease of fabricating these vehicles and even repairing them if they do become damaged, we can get fairly aggressive. So this is an example of trial, I think, 8, where the first 7 were crashes, but using something like iterative learning control, we can learn from past paths and do not just state feedback control, not just sort of typical control. We can actually do sort of aggressive path planning as well. We also can start, the payload for these things is actually fairly high relative to their weight. I mean, it's low in an absolute sense, but we can start to develop other systems to put on board. This is an example of an electro adhesive patch to assist with, I don't know why this isn't playing, but to assist with perching on more or less arbitrary surfaces. And the motivation for this is just simple. The energetics of flight at these scales are extremely expensive energetically, and so anything you can do to sort of save power or recharge or whatever would be welcome. So I am, and there it is. I want to move on slightly. You're probably asking, well, what about the tether and what about power and what about onboard control? I'm going to save that slightly because there's some results which are under review now that I don't want to give away, but we can integrate a number of different sensors. We've closed the loop with a number of different sensors. We have power solutions, and hopefully you'll see that soon. Very related, though, we don't just work on flight systems, we work on legged micro-robots as well. This is an example that my students call it HAMMER, the Harvard Ambulatory Micro-Robot, mostly because they want to do the hammer time thing every time they say it. So we use the same sort of processes to make these legged systems, and they're fabricated in a very similar way. They're slightly larger. The payload is slightly larger for these systems, so we can actually make these things fully autonomous. We can make these things. Well, I'll show you. So we can have these things running around. This is something that's, I don't know why this is playing either. We can make these things be programming in. We can put sensors on board these things to do various tasks, etc. Again, I don't know why this isn't playing. Sorry, but run around, do things typical to larger scale robots, etc. So they're also quite robust in terms of their in their physical structure. Again, for similar reasons. So we can be pretty aggressive with them, pretty brutal with them. They've run off tables and we throw them off things, no problem. Another thing that's and here's an example. They're also pretty energetic devices. Their sort of strength to weight of the actuation system, their power densities are actually relatively high, similar to the RoboBee example I just showed you. There's no real point to these gates. These are sort of corner cases for gate studies that we've been doing. But one interesting thing that I also want to illustrate is that for all of these sorts of small-scale robots, as you get smaller, gravity starts to matter less. And in fact, of course, surface area to volume ratio says that my surface effects are going to start to dominate my dynamics. And so, well, that could be good or bad. And we've decided to work with Rolls-Royce to create similar legged devices, which, by virtue of electrostatic adhesive pads, which you can kind of see on the top here, and is illustrated better here, we can now cling to, now it's conductive but working on non-conductive surfaces, and we can get robots then of this scale to climb up walls and ceilings, albeit very slow, but nonetheless we can get robots to climb on the inside, for example, of a jet engine. The idea there is to do internal inspection, do things which would be very non-invasive, just having things run around inside, look for cracks, carry a camera, whatever. These are all now totally feasible things to do. Here's it. This is a video. If it's supposed to be showing that this video is upside down. There's some artistic value here that I don't really get, but nonetheless. But this is a video which is actually upside down, and the thing is supposed to showing you the gravity vector, but this is walking upside down. All right, so okay, so we can make all these sorts of things, and it's fun to play around with them. They turn out to be also fantastic platforms for studying various biological phenomena as well. We work with a bunch of biologists frequently to try to leverage some of these techniques to make sort of robust and sort of faithful reproductions of some of the structures you might see in nature. We think about these as physical models. One of the nice things about the processes that I described to you, and then I'll stop, is that usually if I think about the complexity of a robot, maybe it's defined by the number of active degrees of freedom or whatever your metric would be. If I start to scale that down, typically you're probably going to decrease your sort of physical complexity. But we don't suffer that. We've made robots that are a few centimeters long that have 40 actuators, so that's fine. We can get fairly faithful reproductions if we wanted to of some organisms. All right. Speaking of some organisms, I want to shift gears entirely to the first topic in soft robotics that I wanted to tell you about, and that's this. So this is a video that hopefully plays.
Zoom out. I'm not sure he's going to swim anymore.
So I actually wanted you to hear the audio here.
There he goes. And it's sideways. He's swimming. I told you he'd swim sideways.
So this is exactly what you imagine it is. So this is an echinoderm. This is actually faster than I would have expected a brittle star to move. But nonetheless, this was and is the state of the art in robotic manipulation for the deep sea. And so what's happening here is some colleagues of ours are attempting to do some sampling at the bottom of the ocean. I'm not sure where this is, but they're trying to delicately sample organisms, put them in a collection tray, bring them back up to the surface and study them. And so that sounds great, but when you have something that is jaws of life looking here, entirely metal, and actually a lot of the technology here is drawn from the oil and gas industry for turning big valves underwater, et cetera. So it's not at all conducive to the types of things that we want to do with respect to delicate sampling. And so here's another example. This is of a glass sponge where we have, it's kind of, yeah. So what you see is what you get here. And what we want to do is, when I saw these videos, I said, well, wait, we can probably do better by applying some of the techniques that we were developing at the time, this is a few years ago now, with respect to soft manipulation. And another thing to note that I think is important here, and part of the theme that I'll come back to in a minute, is well, it's not only do we want to get these things intact, and we want to do this gently. And the reason for that is quite simple. I mean, as you sort of stress these organisms out, they express different genes that aren't representative of their sort of natural lives and their natural habitats, and they don't really tell you everything that's going on with the organism. They don't give you a clear picture. So we want to get something intact and undisturbed. The other thing is that that you know, some of these organisms, I'm not sure about this one, can be hundreds if not thousands of years old. So we want to really be respectful of the ecosystems that we interact with and not just go and sort of maim everything. But at the time, as I was saying, we were developing techniques for soft actuation, and these are quite old now, and there's nothing particularly interesting about them at this point, other than I think it illustrates kind of nicely this thesis of the mechanical side of artificial intelligence, because these are the thing that's showing on the left here are just elastomeric bladders. And by virtue of some inextensible fibers or sheets that we put within them during the molding process, we can get take simple extension, and we can turn that into extension bending, extension twisting, bending twisting coupling, or any combination thereof. So we can get fairly complicated motions just by a single pressurized inputs. And so that's being sort of illustrated here with this sort of anthropomorphic hand that can sort of grasp things. And that was the state of the art at the time. And we said, well, hold on, biologist friends, like let's try to do something like this in the deep sea. And so we did, and we pitched it to the National Geographic Society, and they liked it. We took my colleague's remotely operated vehicle with the soft hand here to Israel a couple years ago. This is us. This is a sort of shameless plug to keep our sponsors happy. But you can see the hand here that I'll show in a moment. And so this is it in operation. So this is the first delicate grasp using what we call these squishy robot fingers. And you can imagine okay, so you see what's just happened there. So I take this actuator, I pressurize it. I'm just doing this with seawater, so I don't have to worry about any sort of hydraulic engines. I just have an open seawater engine. I'm using materials here which are totally impervious to the types of temperatures, pressure, and corrosive nature of the environment which they're operating. And even if they weren't, they cost almost next to nothing. We bring boxes full of squishy robot hands all over the world, which is this is something you ask your postdoc to do and handle the customs part of this. But just to illustrate what's happening here, so basically I get close enough to this sort of whip coral species that I want to sample, and I'm not really doing any control. I just get close enough, and all I have is really visual feedback. And I turn it on. It pressurizes it by virtue of the inextensible fibers that I have in a helical motion, or in a helical structure in the actuator. I get a helical motion out, and that wraps around, and I can come and cut it and take it with me. You can contrast this then to the previous gripper that I showed, which is this sort of metal gripper. And now, imagine I've got, if I want to do a pinch grasp on something like this, and I've got no feedback other than visual, very nice visual feedback. They have great cameras on these ROVs. But that's it, and it's only a 2D camera image, and I'm perhaps a kilometer or two above this on a boat that's sort of rocking, and I'm teleoperating this, and basically doing a successful delicate pinch grasp using that technique would be basically impossible. So we're excited about this. We can also do other form factors, like this is sort of I guess a broccoli-looking coral species that we can do more of a power grasp on. Pretty delicate, and then again come and clip it and take it away. We furthered this, and so again, there's other aspects of this which I'm not really getting into, but we use an open-celled foam on the palms of these hands, such that we can get some effective force feedback, some effective force control, just by virtue of the materials. The materials have a relatively flat force displacement response, so we can get sort of contact force feedback for free. So again, coming back to these use of materials to do what otherwise would need sort of active feedback control for. After that expedition, we were fortunate enough to team up with several research vessels. This is the Nautilus. This is Bob Ballard's boat. He's has quite an enterprise. This is ROV Hercules, and this is now taking off the coast of California. This is now much deeper. The videos I just showed, by the way, were only a couple hundred meters deep in the Red Sea. This is off the coast of California now, about 1,800 meters deep. So again, pressure doesn't really matter for these things. It's just limited by the ROV itself. This is an interesting example now, and I'll come back to this, but you can kind of get what's going on here. You have the typical arm that I showed you previously, but the arm is gripping a gripper. So the gripper is basically on a ball at the end of a stick, and then the soft part is at the most distal end. This is grabbing a Holothuria. This is a sea cucumber, which is about the consistency of wet tissue paper. So you can imagine trying to do this with a more rigid gripper. The other thing that the characteristics of these animals is that they have a defense mechanism by which they invert their stomachs if they're frightened, sort of a take my wallet and leave me alone kind of a thing. And that's not being seen here at all. So we can easily pick up and put down. The other nice thing is that we don't just have to grasp things which are entirely delicate. We can get brittle organisms, but also dynamic organisms like this crab. And maybe I'll fast forward because it takes a while for, yeah, but you get the idea. And you're kind of hearing the ROV pilots talk to each other, and some of the things that that come up anecdotally are like, oh, we'd never be able to do that with our rigid system. So, and we can do. There's other things we could do as well, snails and sea stars, etc. That I'll bore you with. I won't bore you with all that. Then we took this that was all unmanned ROVs. We took this in a manned submersible, and the point of this was to try to advance the system, not just to think about the hand, and the hand not just in a sort of modular way, but also now do an entirely soft arm, which you're kind of seeing here. And there's other subtleties about this work too, which is that we had a rudimentary teleoperation system where the pilot of this arm was wearing a glove that was outfitted with soft sensors that could then control the motion of the manipulator and the sort of closing of the grasp by virtue of the motion of supposed to be more natural motion of the operator's hand. You can kind of see that a little bit here as we're going along. What we're able to create, in this case, this is just a modular system where we're able to sort of in between dives piece together modules of these soft arms. And one of the reasons we wanted to do the soft arms as opposed to the rigid arms was partially for reasons of dexterity and understanding how we could sort of optimize the workspace to achieve dexterity to collect as many things as we wanted to collect. The other one was that we noticed, and you probably saw it when they were reaching for inside the sort of that little crevice for that crab, is that they were banging into things all the time, right? So they were banging into the reef structure or whatever's around the rock, potentially damaging organisms there as well. So that was successful, and we're able to collect things like this midwater pyrosome as well. And yeah, okay, so that's great.
You're under very large pressures, and water is roughly incompressible. I question whether those things are really soft rather than kinematically appropriate for the task.
Soft or kinematically appropriate for the task. Well, it's kind of.
Bends in a nice little circle around the squishy thing.
Yep.
But I bet if a human diver went up and poked at it with his finger, he'd say, "Oh, that's not soft."
The actual organisms, you mean?
No.
The fingers?
The elastomer filled with high pressure water, unless it really has an open exhaust valve to the outside, it's going to be very stiff.
Perhaps, but the other thing that we do is we line the outer surfaces of the fingers themselves with an open cell foam. So that has nothing to do with the fluids, because the fluids can flow in and out. And so you're just getting compression based upon the shore durometer 30A foams that we put on the outside as well. But point well taken. Related to that, I think, is now perhaps you would damage the organism by virtue of these hands, whether it's by virtue, but because of the types of things that we're talking about or not. The other thing that this harkens back to is we want to go collect these organisms, bring them back up to the surface, and study them. That kills them, of course. And so we went on a more recently out with the Monterey Bay Research Aquarium and Institute in the Monterey Bay in California, and deployed this alternative concept, which is now to do sampling by taking this. This is not soft now. This is a structure which is we call this a rotary actuated dodecahedron, which is rad. To actually enclose an animal and then release. Okay, so this is just showing a midwater animal. This is an octopus, but and more or less, other than spraying ink because he's pissed off that we disturbed him, he's unharmed. So the idea here, this is just a preliminary proof of concept of something that we're starting to ramp up now. But the idea is, can we sort of bring the entire lab down into the ocean? Can we outfit these sorts of structures with chemical sensors or cameras for morphometrics or even kinematics? Can we outfit them with genomics suites as well, so we can actually sample some non-destructively sample some of their genetic material and then let them go? All right, so I'm going to switch gears one last time to the last question that I was talking with my colleague Jennifer Lewis, who I'm sure many of you know is a world leader in additive manufacturing, about this following question: can we make entirely soft robots? And what I mean is that, so any of the robots that I've showed you, and most of the things that have come out of our lab and other labs, may have soft actuators or soft end effectors or whatever, but at some point in the chain, you have rigid systems, whether it's a pump or a battery or traditional electronics or whatever. So can we get away from that? This is more of a philosophical thing, I will admit, and this is not pointing to any sort of direct application. There's probably no reason that you'd want to do this at this moment other than answering this question, but I'm going to tell you about it nonetheless. So, so the first set of, so if we can make an entirely soft robot, what would we need to do? And this was sort of boiled down into the following questions. I've already showed you how to make soft actuators. That's not new. I haven't told you about soft sensors, but we can do that too. Mixed phase fluid elastomer sensors, whatever. We can do that too. The things that we really haven't really told you about are, well, how do we make a power system soft, and how would we make a control system soft? And control I'm using very loosely here. And so for that, for those two answers to those two questions, we studied the following. We used a very simple chemical reaction, which is just a monopropellant decomposition in the presence of a catalyst, in this case hydrogen peroxide decomposing into hot oxygen and hot water vapor. And so that's perfect. So if we take a relatively high energy dense fuel, in this case, which is something that has, depending upon how diluted this is fairly high test hydrogen peroxide. This is not the stuff that you clean off wounds with. Then you can get energy densities on par, if not better, than batteries, and you can then create what exactly you need, which is compressed gas, which is high pressure gas. So that would then power our downstream actuators. But then this is a very unregulated open loop reaction. How can we deal with that? And so for that, we turn to microfluidics, and in particular, there's a long history, it turns out, with creating, of course, microfluidic systems using techniques in soft lithography and other microfabrication techniques to do very complicated things with cell sorting or parallel chemical reactions, even emulating now human organ level systems on these sort of microfluidic chips. And so there's a tremendous amount of work that's been done developing systems like this. This is one example that we took inspiration from, if not directly copied, which is a fluidic oscillator. So if I take a single constant pressure input into this system, then it oscillates the output to two different output channels. Okay, so it's a very simple structure, but it's the first sort of example of a broader class of things that we can do. In fact, it turns out that we can do almost the fluidic analogy of almost any electrical system, down from the component level up to systems like comparators and sequencers and shift registers, et cetera. So it's a rich set of things we can do, and then we can also, in the future, hopefully rely on the sort of electrical circuit design tools that have been developed over the past 100 years to help us along this path. But for now, I'm just going to be talking about a very simple control circuit, which is a fluidic oscillator. And so the system I'm about to describe looks like it's schematically represented as follows. So I've got, I inject with fuel. In this case, I have two fuels, but that doesn't really matter. That goes through a microfluidic controller, which is just this oscillator, which basically distributes then downstream the fuel to a catalyst site, which is basically I'll show you, it's a platinum-laden elastomer catalyst that decomposes based upon the reaction I showed you earlier into pressurized gas that then actuates actuators further downstream and then vents to atmosphere. So that's all well and good, but how do we make this? So this is where some innovation came in from the Lewis group, where they at the time, this is a couple years ago now, but they at the time were developing a process called embedded 3D printing. And that's being illustrated here, where now I have in step one here, I've got my fluidic oscillator, which is created using a standard soft lithography technique. I put that upside down in an upside down mold. I fill that mold then with an elastomer, with an uncured elastomer. And what's happening here now is the embedded 3D printing process, where I inject a sacrificial, they call it a fugitive ink. And if they get the rheologies right, and there's all sorts of magic associated with getting the rheologies correct, then that fugitive ink after printing is stable despite the fact that both the fugitive ink and the matrix are uncured. And so then what I can do then is cure the entire thing after this is done. And you can kind of see what's happening here. It's dyed fluorescently so that I can, so you can visualize it. But I get the vasculature basically and actuation sites for this thing. So then I take this, I cure the whole thing, and then by virtue of the nature of this, the ink that they use for the fugitive ink, it's called a pluronic material. It basically undergoes a reverse phase change, breaking down into water. The water evaporates naturally through the porous, in this case, silicone elastomer matrix. And so now I've got these empty channels that serve as the vasculature for what we call the octobot. And you can kind of see all the key features here, you know, actuation sites, and you can kind of make out a little bit the internal guts of this. So here it is illustrated a little bit better, where you've got the inks, the various inks, just two in this case, one for creating the vasculature, one for creating the catalyst site, fluid reservoir, body matrix. And then I've got a bunch of other things in here. I've got a reservoir for where the fuel will be injected. I've got my microfluidic controller, et cetera. So here's what this thing looks like. If I start this up, I inject, this is sped up by a factor of 4 or something, I can't remember. I inject fuel, and then I cut the fuel line, so it's entirely untethered. And then the reaction happens. I sort of, if you squint your eyes, you can kind of see which channel is being, fuel is being delivered through. And then I basically go from this to this. And so we were super excited about this because this was the first entirely soft robot, if you will, that was able to do something which is a very trivial thing, which is just flailing its limbs. But nonetheless, it sort of showed this sort of end-to-end system, and it answered this question: can we make an entirely soft robot? Yes. But usually when I show this this result, and especially at a place like CMU, I would say, well, is that a robot? To which you would say, hell no. And I say, okay, well, I'm going to come back to my original thesis. This is coming back to the definition of that I had for the sort of mechanical side of artificial intelligence or morphological computation, whatever you want to call it. Who's here is familiar with this? This is called an automata. Anybody seen this? This is something that's fantastically, I mean, it's basically a kinetic sculpture, which was created, unsurprisingly, by Swiss watchmakers, and this was done several hundred years ago. And by virtue of a complicated gear cam network, it can write out passages of text, simple passages of text. Is that a robot?
Yes.
Yes. He's the first person to ever say yes to that question. Thank you. Okay. That helps actually my point, but yeah, I mean, you know, whether that's true or not might be debatable. It doesn't have any reactive behavior. It's not really programmable at whatever your definition of a robot might be. But if I were to take a Baxter, or whatever your favorite robot arm is, and put a pen in its hand and, you know, do all of the sort of joint level control and path planning, et cetera, to have it write out the same passage of text, that's a robot, right? So I guess I'm trying to raise a philosophical point here is, at what point could we implement, so could we change around the sort of control architecture that we have? We can make as many actuators and study whatever body form factors you want, but in terms of the behavior, how can we enrich the behavior of devices like this away from this sort of simple example that we have here? And like I said before, there's examples in microfluidic systems that are far, far more complicated. You know, we have something, if we think about valves the way we think about transistors in terms of complexity, you know, we have maybe 4 or 6 here, I can't remember. And there's examples with many thousands. We could, you know, hypothetically encode much richer behaviors and start to really push these sort of mechanical systems, purely mechanical systems, to have more robot-like features. And that's something that we're currently interested in and working on. I'll just give a quick plug to a recent result that we had sort of along these lines, which is this is a device that is, again, there's no real points to this device. It's actually just supposed to be illustrating a new process that we developed by which we can create now an analogy. So this Popup book inspired process that I showed you to make these small robots, now we're able to do this with soft materials. And so we're able to do this with soft materials using now a combination of multilayer soft lithography and bulk laser micromachining now of these silicone-based elastomer materials. And this allows us to create, this is just a mock-up of a peacock spider. But the idea is that I can have, by virtue of the fact that I can have very dense networks of microfluidic channels, I can create, you know, highly articulated structures at very small scales in entirely soft materials. We also have some work, one of the questions you might have is, well, that's great, but you know, what's behind the curtain here, which is a whole bunch of hydraulic lines. But we can also do things, again, electrically analogous to multiplexers and demultiplexers to actually have these things be controlled by a small number of parameters. The other thing I want to point out, which I think is really cool about this process, which is it was kind of hard to see, is if I can create actuators in these sort of multi-layer soft lithography microfluidic networks, and they're very simple. I just basically have a unpatterned side and have a patterned side with a gap in it, and if I pressurize that gap, then it bends towards the other side. Okay, so very, very sort of simple actuation architecture. But now if I actuate that with water or some other liquid or fluid, I can actuate that repeatedly. But if I actuate that with, for example, an uncured version of my elastomer, and then cure that, for example, with heat or UV light, then I freeze it into its three-dimensional shape. So I can get things which sort of pop up into 3 dimensions again and can get frozen into that shape. Or not, or I can make mechanisms in the same way. And so this is some interesting recent work. I'm gonna stop there because I think we're out of time, but I do want to give a couple of plugs to some other work that we have in related areas, and this is just a sampling, and I apologize to my students, this is not a complete sampling, but we do a lot with soft actuators, as I was sort of describing, but I feel like the holy grail with soft robotics, and perhaps, what my view, all of robotics, is to come up with muscle-like actuation that's electrically activated. And so we've got a lot of work recently, and there's a new paper which I didn't have time to include here that just came out describing multi-layer dielectric elastomer actuators that have many thousands of layers that are in exactly muscle-like form factors that don't require, so what are the downsides of dielectric elastomers historically have been? They require tremendously high fields, they require pre-stretch, which typically leads to rigid frames, and they require strain-compatible electrodes. And so we've solved all of these by creating processes, by using elastomers which don't, by virtue of their chemistry, don't require pre-stretch in order to achieve high strains without the sort of pull-in instability that is typical. We can make these in a liquid form, so we can spin cast them or draw cast them or doctor blade them so that we can create extremely thin layers, thereby lowering for a given field, lowering the voltage requirements to get them down from tens of kilovolts down to maybe a couple hundred volts and shrinking. And lastly, we use a combination of carbon nanotube, sparse carbon nanotube and silver nanowire electrodes, which don't interfere with interlayer adhesion and have negligible effect on the overall size and stiffness of the actuator. Sorry, that was long-winded. But we can make muscle-like actuators now with energy densities on the order of tens of joules per kilogram and human-like bandwidth. So we're very excited about that. And efficiencies is hard to quantify. They're decent. We make soft robots that you can run over with cars. That's not super interesting anymore. Some of these are 2 examples of work where we leverage some of these sort of folding-based structures to create robots, but now having it be self-folded in this case, something that sort of starts as a flat structure that you throw a whole bunch of guts on and then it folds itself up and walks away. That was work with Daniela Roos and Eric Demain at MIT. Similarly, with that same group, this is an older program where we had the idea to do the same thing but have it be reconfigurable, so it folds itself into one thing, then it folds itself into something else, kind of like the Swiss Army knife based upon origami-like patterns. 3D printed jumping soft robots, soft sensors that we can create in sort of arbitrary form factors and get surface tractions, normal forces, and in-plane forces, stresses. This is a relatively new work where we are using fluidic soft actuators, but now we're using vacuum as opposed to positive pressure and sort of origami-like internal skeleton to guide motions. And so we can create very complex, entirely soft things. And the fact that we're using vacuum actually makes them safe. And the last thing I'll say is this is part of a MURI, which Zeynep has been a participant in, where we're looking at some of these techniques to make small-scale, highly dynamic structures as physical models for studying biological mechanisms, in this case, ultra-fast motions and power amplification mechanisms that arise in things like mantis shrimp, which this is supposed to be emulating, but also just sort of generic jumping and punching types of things. Okay, so I'm going to stop there, and I guess there's maybe a time for a few questions. Thank you. Yeah, it's a great question. So the question is how easy or difficult is it to design some of these scaffolds that control motion? Extremely difficult. And so it kind of tipped the balance. So that prior to that, the designs were trivial, but the fabrication was extremely difficult. And so it really flipped that, where now the fabrication is just like a cookbook, but the design of it is tremendously difficult. We've made a little bit of headway on that by developing some custom sort of CAM software, CAD CAM software, to try to, it's called Popup CAD, in case you're interested. To try to sort of hide some of the low-level operations and do design rule checks and that sort of thing. It's very much a work in progress, but you can make it a little bit easier, but yes, it does require skill. Well, another thing that we do typically, which you kind of gathered, is we also make things on larger scales, so we can sort of prototype using not fancy UV laser micromachining systems and high-performance composite materials and whatever. We can make cardboard and plastic and CO2 laser stuff and test out things like the kinematics or whatever on those scales. Yes.
Can you speak about the relationship between morphological computation and some of the work in modeling and controlling these systems from more traditional
Or first principles? Yes. So, I mean, in the end, I don't want to use this as a sort of a cop-out. I don't want to say like, oh, just make your robot soft and you don't have to worry about contact anymore, right? Because that's not true. I think that my argument is that it might make things easier. It might make things like highly discrete events, right? Or I should say discontinuous events like contact, making or breaking contact, maybe a little bit easier, to model. But all of that aside, we spend a lot of our effort trying to model these things and ask questions about, if we were to control the motion of whatever this thing is. And I'm only really showing you very simple examples where I'm bending something, and so that's kind of a trivial thing. But for more complicated systems like we're kind of working on now, I didn't describe this, but wearable systems that might interact with a human, or many degree of freedom things. We do have a tremendous amount of work, and this is with some of our colleagues at Harvard and elsewhere on modeling the systems such that we can do, maybe it's first principles or maybe it's numerical, whatever, to give us some insights for how we might want to control these things. So I don't think it's one or the other. I think it's very much a marriage of the two. Yes, Chris.
At some level, your timing is terrible because
Story of my life.
You're saying, oh, let's not have any brains. We finally have figured out through reinforcement learning how to do model-free behavior generation for systems that are way too complex to model. So why not embrace the machine learning thing and say, okay, I'll have some relatively simple computer running some relatively simple, essentially analog computing thing.
Yeah. No, that's a great point. And in fact, that's what we're doing. So we're, again, I didn't get into the stuff we're doing with wearable systems, but I'll use that as an example. We have developed in the past and are developing now, like wearable sensors that you might want to put in your clothes so you can get motion tracking or diagnostics or gaits or whatever you want to do. So it's a tremendously hard question. I was also trying to pose earlier is where would I put these sensors and how would I make sense of the information that comes from them? There's no way I'm doing that out of first principles. And so we'd slap a machine learning algorithm on it and it works really well. But that doesn't, I'd still make the argument that if you want to have something, anything, for example, human-centric, that that I want to have doing something interesting, then the properties of being soft or taking away some of the burden of really understanding the nuances of deformations or contact or whatever would be potentially beneficial to those algorithms. That's a great point. Yes.
That kind of reminds me of the experience of the Berkeley group when they were in body cognition. Sri Narayana came in, gave them a robot, they plugged the robot in, and simply the placement of the joints did the computation that they'd never been able to figure out how to do it.
Yeah.
Go all the way to the human body and just see if it still works.
Yeah. I don't know if this is directly related, but when I teach a robotics class, one of the things that we look at are simple manipulator equations for standard robot arms, right? And ask the question, well, how do these things evolve to be this way? And part of the reason is because they were computationally easy to study if you arrange them in a certain way, right? And so, yeah, I think that there's maybe to Chris's point, maybe that's going away as computation gets easier and cheaper and et cetera. But nonetheless, that's the course of evolution. Yeah.
I was just curious, how do you identify the characteristic resonant modes of the robot?
It's relatively simple tests. So I was describing really two modes, this sort of flapping mode and this rotational mode. Of course, there are many more. We try to get around really studying all of these sort of aeroelastic interactions just by, this is kind of one instance where we can do better than biology in terms of materials. We can get higher stiffness to weight, for example, than any biological material by using carbon reinforced materials. And so we basically just make a wing as low inertia but as high stiffness as possible so that we kind of can approximate just with these two modes. And then we just experimentally, determine this, mostly visually. Yep. We some vibrometry as well, but mostly visually.
No more questions?
Thank you. Thank you.